So in this lecture, we're going to drill down into our first specific search strategy for graphs and also explore some applications, namely breadth-first search. So let me remind you the intuition and applications of breadth-first search. The plan is to systematically explore the nodes of this graph, beginning with the given starting vertex in layers. So let's think about the following example graph, where S is the starting point for our breadth-first search. So the start vertex S will constitute the first layer, so we'll call that L0. And then the neighbors of S are going to be the first layer, and so those are the vertices that we explore just after S, so those are L1. Now the second layer is going to be the vertices that are neighboring vertices of L1 but are not themselves in L1, or for that matter, L0. So that's going to be C and D. That's going to be the second layer. Now you'll notice, for example, S is itself a neighbor of these nodes in layer 1, but we've already counted that in the previous layer, so we don't count S toward L2. And then finally, the neighbors of L2, which are not already put in some layer, is E. So that'll be layer 3. Again, notice C and D are neighbors of each other, but they've already been classified in layer 2, so that's where they belong, not in layer 3. So that's the high-level picture of breadth-first search you should have. We'll talk about how to actually precisely implement it on the next slide. Again, just a couple of the things that you can do with breadth-first search, which we'll explore in this video, is computing shortest paths. So it turns out shortest path distances correspond precisely to these layers. So for example, if you had as S, you had that as the Kevin Bacon node in the movie graph, then John Hamm would pop up in the second layer from the breadth-first search from Kevin Bacon. I'm also going to show you how to compute the connected components of an undirected graph, that is, compute its pieces. We'll do that in linear time. And for this entire sequence of videos on graph primitives, we will be satisfied with nothing less than the holy grail of linear time. And again, remember, in a graph, you have two different size parameters, the number of edges m and the number of nodes n. For these videos, I'm not going to assume any relationship between m and n. Either one could be bigger. So linear time is going to mean O of m plus n. So let's talk about how you'd actually implement breadth-first search in linear time. So the subroutine is given as input both a graph, G. I'm going to explain this as if it's undirected, but this entire procedure will work in exactly the same way for a directed graph. Again, obviously, in an undirected graph, you can traverse an edge in either direction. For a directed graph, you have to be careful only to traverse arcs in the intended direction, from the tail to the head. That is, traverse them forward. So as we discussed when we talked about just generic strategies for graph search, we don't want to explore anything twice. That would certainly be inefficient. So we're going to keep a Boolean at each node, marking whether we've already explored it or not. And by default, we're just going to assume that nodes are unexplored. They're only explored if we explicitly mark them as such. So we're going to initialize the search with the starting vertex S. So we mark S as explored, and then we're going to put that in what I was previously calling conquered territory, the nodes we've already started to explore. So to get linear time, we're going to have to manage those in a slightly non-naive, but pretty straightforward way, namely via a queue, which is a first-in, first-out data structure that I assume you've seen. If you've never seen a queue before, please look it up in a programming textbook or on the web. But basically, a queue is just something where you can add stuff to the back in constant time, and you can take stuff from the front in constant time. You can implement these, for example, using a doubly linked list. Now recall that in the general systematic approach to graph search, the trick was to, in each iteration of some while loop, to add one new vertex to the conquered territory, to identify one unexplored node that is now going to be explored. So that while loop is going to translate into one in which we just check if the queue is non-empty. So we're assuming that the queue data structure supports that query in constant time, which is easy to implement. And if the queue is non-empty, we remove a node from it. And because it's a queue, removing nodes from the front is what you can do in constant time. So call the node that you get out of the queue V. So now we're going to look at V's neighbors, vertices with which it shares edges, and we're going to see if any of them have not already been explored. So if W is something we haven't seen before, if it's unexplored, that means it's in the unconquered territory, which is great. So we have a new victim. We can mark W as explored, we can put it in our queue, and we've advanced the frontier, and now we have one more explored node than we did previously. And again, a queue, by construction, it supports adding constant time additions at the end of the queue, so that's where we put W. So let's see how this code actually executes in the same graph that we were looking at in the previous slide. And what I'm going to do is I'm going to number the nodes in the order in which they are explored. So obviously the first node to get explored is S. That's where the queue starts. So now when we follow the code, what happens? Well, in the first iteration of the while loop, we ask, is the queue empty? No, it's not, because S is in it. So we remove, in this case, the only node of Q, it's S, and then we iterate over the edges incident to S. Now there are two of them. There's the edge between S and A, and there's the edge between S and B. And again, this is still a little underspecified in the sense that the algorithm doesn't tell us which of those two edges we should look at. Turns out it doesn't matter. Either of those is a valid execution of breadth first search. But for concreteness, let's suppose that of the two possible edges, we look at the edge S comma A. So then we ask, has A already been explored? No, it hasn't. This is the first time we've seen it. So we say, oh, goody, this is sort of new grist for the mill. So we can add A to the queue at the end, and we mark mark A as explored. So A is going to be the second vertex that we mark. So after marking A as explored and adding it to the queue, so now we go back to the for loop, and so now we move on to the second edge incident to S. That's the edge between S and B. So we ask, have we already explored B? Nope, this is the first time we've seen it, so now we do the same thing with B. So B gets marked as explored, it gets added to the queue at the end. So the queue at this juncture has first a record for A, because that was the first one we put in it after we took S out, and then B follows A in the queue. And again, depending on the execution, this could go either way, but for concreteness, I've done it so that A got added before B. So at this point, this is what the queue looks like. So now we go back up to the while loop. We say, is the queue empty? Certainly not. It actually has two elements. Now we remove the first node from Q. In this case, that's the node A. That was the one we put in before the node B. And so now we say, well, let's look at all of the edges incident to A. And in this case, A has two incident edges. It has one that it shares with S, and it has one that it shares with C. And so if we look at the edge between A and S, then we'd be asking in the if statement, has S already been explored? Yes, it has. That's where we started. So there's no reason to do anything with S. That's already been taken out of the queue. So in this for loop for A, there's two iterations. One involves the edge with S, and that one we completely ignore. But then there's the other edge that A shares with C, and C we haven't seen yet. So at that part of the for loop, we say, aha, C is a new thing, new node we can mark as explored and put in the queue. So that's going to be our number 4. And so now how is the queue changed? Well, we got rid of A, and so now B is in the front, and we added C at the end. And so now the same thing happens. We go back to the while loop, the queue is not empty. We take off the first vertex, in this case that's going to be B. B has 3 incident edges. It has one incident to S, but that's irrelevant. We've already seen S. It has one incident to C. That's also irrelevant. That's also relevant because we've already seen C. True, we just saw it very recently, but we've already seen it. But the edge between B and D is new, and so that means we can take the node D, mark it as explored, and add it to the queue. So D is going to be the 5th one that we see. And now the queue has the element C followed by D. So now we go back to the while loop, and we take C off of the queue. It again has 4 now edges. The one with A is irrelevant, we've already seen A. The one with B is irrelevant, we've already seen B. The one with D is irrelevant, we've already seen D. But we haven't seen E yet. So when we get to the part of the for loop of the edge between C and E, we say, aha, E is new. So E will be the 6th and final vertex to be marked as explored. And that will get added at the end of the queue. So then in the final 2 iterations of the while loop, the D is going to be removed. We'll iterate through its 3 edges. None of those will be relevant because we've seen all of the other 3 endpoints. And then we'll go back to the while loop and we'll get rid of E. E is irrelevant because it has 2 edges. We've already seen the other endpoints. And now we go back to the while loop. The queue is empty and we stop. And that is breadth first search. And to see how this simulates the notion of the layers that we were discussing in the previous slide, notice that the nodes are numbered according to the layer that they're in. So S was layer 0, and then the 2 nodes that S caused to get added to the queue, the A and the B, are numbered 2 and 3. And the edges of layer 3 are precisely the ones, the edges of layer 2 are precisely the ones that got added to the queue while we were processing the nodes from layer 1. That is, C and D are precisely the nodes that got added to the queue while we were processing A and B. So this is level 0, level 1, and level 2. E is the only node that got added to the queue while we were processing layer 2, the vertices C and D. So E will be the third layer. So in that sense, by using a first in, first out data structure, this queue, we do wind up processing the nodes according to the layers that we discussed earlier. So the claim is that breadth first search is a good way to explore a graph, in the sense that it meets the two high-level goals that we delineated in the previous video. First of all, it finds everything findable, and obviously nothing else. And second of all, it does it without redundancy. It does it without exploring anything twice, which is the key to its linear time implementation. So a little bit more formally, claim number 1, at the end of the algorithm, the vertices that we've explored are precisely the ones such that there is a path from S to that vertex. And again, this claim is equally valid whether you're running BFS in an undirected graph or a directed graph. Of course, in an undirected graph, we mean an undirected path from S to V, whereas in a directed graph, we mean a directed path from S to V. That means a path where every arc in the path gets traversed in the forward direction. So why is this true? Well, this is true. We basically prove this more generally for any graph search strategy of a certain form, of which breadth first search is one. If it's hard for you to see the right way to interpret breadth first search as a special case of our generic search algorithm, you can also just look at our proof for the generic search algorithm and copy it down for breadth first search. So it's clear that you're only going to, again, the forward direction of this claim is clear. If you actually find something, if something's marked as explored, it's only because you found a sequence of edges that led you there. So the only way you mark something that is explored is if there's a path from S to V. Conversely, to prove that anything with an S to V, with a path from V will be found, you can proceed by contradiction. You can look at the part of the path from S to V that BFS does successfully explore, and then you get asked, why didn't it go one more hop? It never would have terminated before reaching all the way to V. So you can also just copy that same proof that we had for the generic search strategy in the previous video. Okay, so again, the upshot, breadth first search, it finds everything you'd want to find. Okay, so it only traverses paths, so you're not going to find anything where there isn't a path to it, but it never misses out. Okay, anything where there's a path, BFS guaranteed to find it, no problem. Claim number 2 is that the running time is exactly what we want, and I'm going to state it in a form that will be useful later when we talk about connected components. So the running time of the main while loop, ignoring any kind of pre-processing or initialization, is proportional to what I'm going to call NS and MS, which is the number of nodes that can be reached from S and the number of edges that can be reached from S. And the reason for this claim, this just becomes clear if you inspect the code, which we'll do in a second. So let's return to the code and just tally up all the work that gets done. So I'm going to ignore this initialization. I'm just going to focus on the main while loop. So we can summarize the total work done in this while loop as follows. First, we just think about the vertices. So in this search, we're only going to ever deal with the vertices that are findable from S, so that's NS. And what do we do with a given node? Well, we insert it into the queue and we delete it from the queue, right? So we're never going to deal with a single node more than once. So that's constant time overhead per vertex that we ever see. So that's the proportional to the NS part. Now, a given edge, we might look at it twice. So for an edge VW, we might consider it once when we first look at the vertex V, and we might consider it again when we look at the vertex W. Each time we look at an edge, we do constant work. So that means we're only going to do constant work per edge. Okay, so we look at each vertex at most once. We look at each edge findable from S at most twice. We do constant work when we look at something. So the overall running time is going to be proportional to the number of vertices findable from S plus the number of edges findable from S. So that's really cool. We have a linear time implementation of a really nice graph search strategy. And moreover, we just need very basic data structures, a queue to make it run fast with small constants. But it gets even better. We can use breadth first search as a workhorse for some interesting applications. So that's what we'll talk about in the rest of this video.